Hey everyone! Welcome back to Future Engineering Lab. Whether you're a subscriber who's been with us from the start, or this is your very first time watching one of our videos, welcome. It's genuinely awesome to have you here in the lab today. In today's video, we're going to build something really interesting and super useful. We're creating a powerful Python-based tool that can take almost any airfoil, modify it by adding a flap and a cavity, and then prepare the geometry perfectly for CFD simulations in ANSYS. So, let's get started. Let's dive right in and engineer the future together. Before we start writing the code, let's take a quick look at how our program is structured. First, we create a class called NACA for Airfoil to generate the airfoil geometry. Then, we calculate the thickness distribution and generate the upper and lower surfaces. After that, we add the Gurney flap to the trailing edge of the airfoil. Finally, we save the coordinates to a file and plot the final geometry. The main program then asks the user for the required inputs and runs all these steps in the correct order. Let's start with the libraries. First, we import NumPy, which we use for numerical calculations and handling arrays of coordinates. Next, we import matplotlib, which allows us to visualize the airfoil and the Gurney flap. Finally, we import the OS module. We use it later to create the path to the user's Downloads folder and save the output file there. Now, let's create a class called NACA for Airfoil. The main purpose of this class is to keep all the airfoil-related operations organized in one place. Instead of writing separate pieces of code for every operation, we can create methods for generating the airfoil, adding the Gurney flap, saving the coordinates, and plotting the geometry. This also makes the code easier to modify and extend later. This is the constructor of our class. It takes the NACA number, chord length, and number of points as inputs. Here, we check if the NACA code contains exactly 4 digits. If the input is not valid, the program raises an error. We store the NACA number inside the class. The first digit defines the maximum camber as a percentage of the chord. The second digit defines the location of maximum camber. The last 2 digits define the maximum thickness as a percentage of the chord. Here, we store the chord length. And here, we store the number of points used to generate the airfoil. These variables will later store the x-coordinates and the thickness distribution. These variables will store the coordinates of the upper surface, and these variables will store the coordinates of the lower surface. Finally, we create empty arrays for the Gurney flap coordinates, which will be filled later. Now let's move to the first method, which calculates the airfoil thickness distribution. We start by generating cosine-spaced points along the chord. Cosine spacing gives us a higher concentration of points near the leading edge and trailing edge, where the geometry changes more rapidly. The formula is, here, beta varies from 0 to pi, and c is the chord length. This gives us a higher point density near both ends of the airfoil, where the geometry changes more rapidly. After calculating the x-coordinates using cosine spacing, we calculate the thickness distribution using the standard NACA 4-digit thickness equation. The equation uses the normalized chordwise position, x over c, and the thickness ratio, t, to calculate the local half thickness at each point along the airfoil. For example, for a NACA 2412 airfoil, the thickness ratio is 0.12. The calculated values are stored in the YT array. Keep in mind that YT represents the half thickness. Therefore, the total thickness at any point is equal to twice yt. At this point, we have the x-coordinates in the thickness distribution. Next, we need to calculate the camber line to generate the final upper and lower surfaces. Now that we have the thickness distribution, we can generate the complete airfoil geometry. First, we normalize the x-coordinate by the chord length. Then, we check whether the airfoil is symmetric or cambered. For a symmetric airfoil, we simply place the thickness distribution above and below the chord line. For a cambered airfoil, we calculate the camber line and its slope using the NACA equations. Here, we create an array of zeros with the same size as the x-array to store the camber line coordinates. Similarly, we create another array to store the slope of the camber line at each point. Now we loop through all the x-coordinates and calculate the camber line and its slope at each point. Here, we check whether the current point is before or after the maximum camber location. For a cambered NACA 4-digit airfoil, the camber line is defined using two separate equations. The first equation is used from the leading edge to the maximum camber location. The second equation is used from the maximum camber location to the trailing edge. The parameter m represents the maximum camber, while p represents its location along the chord. For example, for a NACA 2412 airfoil, the maximum camber is 2% of the chord, located at 40% of the chord. The code checks the normalized x-coordinate and selects the appropriate equation for each point. Finally, we use the camber line angle to offset the thickness distribution and obtain the final upper and lower surface coordinates. Since the camber line was calculated using normalized coordinates, we multiply it by the chord length to convert it into the actual dimensions of the airfoil. Next, we calculate the local angle of the camber line using the arctangent of its slope. Instead of simply adding yt directly to yc, we offset the thickness perpendicular to the camber line. Similarly, we calculate the lower surface by offsetting the thickness distribution in the opposite direction. These equations are used to calculate the final upper and lower surface coordinates of the airfoil. The important point here is that the thickness is applied perpendicular to the camber line, rather than simply adding the thickness in the vertical y direction. This gives us a more accurate representation of the actual NACA airfoil geometry. Here, we define the add Gurney method. It takes 4 inputs: the position, height, thickness, and angle of the flap. We convert the Gurney position from a percentage of the chord to the actual x-coordinate. We convert the flap height from a percentage of the chord to the actual length. Similarly, we convert the Gurney thickness from a percentage of the chord to the actual length. We convert the angle from degrees to radians because NumPy trigonometric functions use radians. Here, we find the index of the upper surface point that is closest to the specified flap position. Similarly, we find the closest point on the lower surface. We store the x and y coordinates of the selected point on the upper surface. We do the same for the lower surface. Next, we calculate the x and y components of the direction vector of the flap. These two components determine the direction in which the Gurney flap extends. Here, we calculate a normal vector perpendicular to the direction of the Gurney flap. This vector is used to define the thickness of the flap. We start from the selected point on the upper surface. We move from the starting point along the Gurney direction by the specified height. Next, we move perpendicular to the Gurney direction by the specified thickness. Finally, we apply the same thickness offset to the second point to create the fourth corner. Now, we repeat the same process, starting from the selected point on the lower surface. We move along the Gurney direction, but in the opposite vertical direction. We create the thickness offset in the opposite direction. Finally, we calculate the fourth corner of the lower Gurney flap. Here, we store all the x-coordinates of the Gurney flap points in one NumPy array. Similarly, we store all the y-coordinates. Since this is a two-dimensional geometry, all 8 z-coordinates are set to 0. Now we define the save-Zuter method, which is responsible for saving all the airfoil and Gurney flap coordinates to a file. First, we combine all the x-coordinates into a single array. We start with the upper surface coordinates, then add the lower surface coordinates in reverse order, and finally add the Gurney flap coordinates. We reverse the lower surface array. This ensures that the points are ordered consistently, so the geometry points follow each other in the correct sequence around the airfoil. Do the same for the y-coordinates, combining the upper surface, the reversed lower surface, and the Gurney flap coordinates. Since our airfoil geometry is two-dimensional, we set the z-coordinate of all airfoil points to 0. Then, we add the z-coordinates of the flap. Here, we open the specified file in write mode. If the file does not exist, a new file will be created. Now, we loop through the x, y, and z coordinates simultaneously. At each iteration, we have one point. Finally, we write each point to the file using 6 decimal places for each coordinate. The output format will be like this. Each point is stored on a separate line. After saving the coordinates, we display the file path to confirm that the coordinates have been successfully saved. The print info method is used to display some useful information about the generated airfoil. It shows the NACA number, whether the airfoil is symmetric or cambered, the maximum camber, the camber location, the chord length, the number of points, and the maximum thickness. This is useful for quickly checking whether the generated geometry matches the input parameters. Finally, we define the plot method to visualize our geometry. This method uses matplotlib to display the airfoil in Gurney flap geometry. First, we create a figure and check if a Gurney flap has been added. If it exists, we plot the upper and lower Gurney flap geometry separately. Then, we plot the upper and lower surfaces of the airfoil. Finally, we set an equal axis scale, add labels and a legend, and display the complete geometry. This gives us a quick visual check before exporting the coordinates and using them in ANSYS. Here we define the main function of our program. This function controls the complete workflow, from getting user inputs to generating the airfoil, adding the Gurney flap, saving the coordinates, and plotting the final geometry. Here, we ask the user to enter the 4-digit NACA airfoil number. The program will use this value to generate, for example, the NACA 2412 geometry. Here, we ask the user to enter the chord length. The input is converted to a floating point number because it can contain decimal values. We ask the user to specify the number of points used to generate the airfoil geometry. A higher number of points gives a smoother and more accurate geometry. The user enters the name of the output file where the coordinates will be saved. We create the path to the user's Downloads folder. The expand user function finds the user's home directory automatically. We combine the Downloads folder path with the file name provided by the user. This ensures that the output file will be saved directly in the Downloads folder. We create an object from the NACA 4 Airfoil class. We pass the NACA number, chord length, and number of points as inputs. From this point, this object contains all the information needed to generate and modify the airfoil. Now, we call the generate method to calculate the airfoil geometry. This step calculates the thickness distribution, camber line, and finally, the upper and lower surface coordinates. We display useful information about the generated airfoil. This includes the airfoil type, maximum camber, thickness, chord length, and number of points. Here, the user specifies the Gurney flap position as a percentage of the chord. The user specifies the height of the Gurney flap as a percentage of the chord. The user defines thickness and angle, too. Then, we call the add Gurney method. This method uses the given parameters to create the Gurney flap geometry and store its coordinates. We save the final airfoil and Gurney flap coordinates into the output file. The saved file can later be imported into CAD or CFD software, such as ANSYS SpaceClaim or ISEM. This condition checks whether the current file is being executed directly. If it is, the main function will run and start the complete workflow. Now, let's test our code and see if everything works correctly. Click anywhere inside the code cell and press Shift plus Enter to run the program in Jupyter Notebook. The program first asks us to enter a NACA 4-digit airfoil. As an example, we enter 2412. Next, it asks for the chord length. Since our geometry is defined in millimeters, we enter 100. Then, we enter the number of points used to generate the airfoil geometry. A higher number of points results in smoother and more accurate curves. In this example, we use 200 points. After that, we provide a name for the output file. The program will save the coordinates as a text file, so any name with the .txt extension can be used. After pressing Enter, the program displays the airfoil information, including the airfoil type, maximum camber location, chord length, number of points, maximum thickness, and its location. Next, we define the Gurney flap parameters. The flap position is usually close to the trailing edge, so a value around 80% of the chord is a reasonable choice. For the flap height, values between 1% and 2% of the chord are commonly used, while the thickness should be very small. For example, 0.2% of the chord is already a reasonable value. Finally, we enter the flap angle. In this example, we use 30 degrees measured from the y-axis. After completing the inputs, the program plots the final airfoil geometry with the Gurney flap, and the coordinate file is saved automatically in the Downloads folder. Now, let's go to the Notepad file and take a look at the coordinates generated by the code. Here is the data. If you remember the data format we discussed in the previous videos, you'll recognize it right away. If you haven't watched those videos yet, you can click the link above and check them out first. This is the upper surface of the airfoil. As you can see, all of its y coordinates are positive. These are the last 2 points at the trailing edge. And this is the lower surface, where all the y coordinates are negative. Finally, these are the 8 points that define the upper and lower Gurney flaps. Since we're preparing this for SpaceClaim 2D, we need to format the data correctly. Go to the Data tab and click Text to Columns. Choose Delimited, then click Next. Select comma as the delimiter instead of tab, and click Finish. The final step is to add a value of 1, which is the curve number or curve ID, in a new column for all of the airfoil coordinate points. This forms a continuous curve. Do this except for the last 8 rows, which correspond to the upper and lower flap coordinates. We want flaps as points. There are 2 possible approaches to do this. The first and most common method is to leave a blank line or cell between consecutive points. By separating the points this way, SpaceClaim treats each one as an individual entity and imports it as a separate vertex. The second method is to assign a different curved ID to every point. The number at the beginning of each row is the curve ID. Normally, points with the same ID are grouped together to form a single curve. However, if every point has a unique ID, such as 1, 2, 3, and 4, SpaceClaim considers each point as a separate entity instead of connecting them into one curve. For most applications, the first method is simpler and is generally the recommended approach. Let's go with the first method as recommended in the ANSYS help documentation. Oh, and one more thing. SpaceClaim 2D doesn't use z-coordinates, so make sure to remove that column first. Now, copy all the data and paste it into a new Notepad file. Save the file, then open ANSYS Workbench. Next, drag a geometry component from the toolbox into the project schematic. Right-click the geometry cell and select New SpaceClaim Geometry. Before importing the file, go to File, SpaceClaim Options, and make sure the length units are set to millimeters. Now switch to the Assembly tab and click Files to import the data. Change the file type to point curves so the text files become visible. Select the Notepad file we saved earlier and click Open. When prompted to select a sketch plane, choose the XY plane. Then press V to switch to plane view and look at the sketch normal to the plane. As you can see, the airfoil has been imported as a smooth, continuous curve with a closed trailing edge, while the Gurney flaps have been imported as individual points. Now go to the Sketch tab and select the Line tool. Connect the flap points by creating each line separately. If you can't select a specific point, go to Sketch Options and make sure Snap to Grid is turned off. This allows you to select points freely instead of snapping to the grid. I still can't set the line angle to exactly 90 degrees by dragging, so I'll press Tab to switch to the angle field, type 90, and then press Enter. Now draw the second line, and when you're finished, press Escape to exit the line tool. Repeat the same steps for the lower flap. You can zoom in at any time by pressing Ctrl+ and zoom out by pressing Ctrl-. As you can see, there's a small gap between the airfoil and the flap at the corner. We can easily close this gap using the Pull tool. Simply extend the flap until it slightly intersects the airfoil. Next, go to Split Curve. First, select the flap, then select the airfoil as the cutting curve. This splits the flap at the intersection. Finally, use Trim Away to remove the extra portion of the flap. Repeat the same procedure for the lower flap. Now, let's create the cavities in the airfoil. Select the Circle tool. I'll temporarily enable Snap to Grid so it's easier to choose an integer value for the x-coordinate. In this case, 35 millimeters looks like a good location. Place the center of the circle there and set the radius to 7 millimeters. Next, select Split Curve. First, click the airfoil curve, then choose the circle as the cutter, and complete the operation. Now select Trim Away and remove the unwanted curve segments. Repeat the same procedure to create the lower cavity. Next, let's clean up the flaps. As you can see, there is an extra curve at the root of each flap. This segment belongs to the original airfoil and should be removed. Use Trim Away to delete these extra segments so that the airfoil, the flaps, and the cavities form a single continuous curve. Once that's done, you can create a hollow extrusion using the Pull tool. Simply drag a selection box over the entire sketch to select all the curves. Then, pull them to the desired thickness. If you want a solid model instead, first, select the entire closed sketch and click Fill to create a surface. Then, use the Pull tool to extrude the surface into a solid body. Finally, you can specify any extrusion depth you need along the Z direction. And before you go, if you'd like to use the same script from this tutorial, I've uploaded it to my GitHub repository. You'll find the GitHub link in the video description. If you found this video helpful, please give it a thumbs up and consider subscribing to the channel for more ANSYS, CFD, and engineering tutorials. If you have any questions, run into any issues, or have suggestions for future videos, feel free to leave a comment below. I'll do my best to answer as many of them as I can. Thanks for watching, and I'll see you in the next video.